Okay, so now we know that a double integral finds us the volume under some surface, but that doesn't help us to evaluate it, to actually find them. So when we want to find them, we want to borrow techniques from when we were doing partial derivatives. When you're integrating with respect to x, you treat y as if it's a constant. And then when you're integrating with respect to y, you treat x as a constant. Now let's put this into practice here. So we're going to evaluate the double integral from 0 to 3, then 2 to 5 of 2x plus 4y dx dy. Oh my goodness. Okay, and then we're going to describe what this means geometrically. Well, let's do the integration part first, and then we'll look at it. Okay, so we want to find the integral from 0 to 3 of. Okay, and then what we're going to do is we're going to take the inner portion and find that integral, this piece. So you're going to integrate this with respect to x because x is your differential here. Dx is your differential. So you want to treat this as if x is your only variable. So the integral of 2x with respect to x is x squared plus the integral of 4y with respect to x is 4yx. Because as far as x is concerned, y is a number. And then we want to integrate that from x equals 2 to x equals 5. The differential being x lets us know those are x values. And then we still haven't done anything with the y, so dy just kind of sits out there on its little lonesome. All right, so we're going to integrate from 0 to 3. Now we're going to put 5 in and then put 2 in. So this would be 5 squared plus 4 times y times 5 minus 2 squared plus 4 times y times 2. Right, so all of that is inside, and we still haven't done the integral with respect to y. So the integral sign stays here, and the dy stays back there. All right, so one more time, let's simplify this inner portion. So this is 25 right here plus 20y, take away 4, and then take away, because this is subtraction to both of these, 8y dy. All right, so then that's the integral from 0 to 3 of 25 take away 4 is 21 minus, oh no, plus 20 take away 8 would be 12y dy. All right. Well, the integral of 21 with respect to y now, because now I can actually do the y portion, the integral with respect to y of 21 is 21y plus 12y squared over 2, which would be 6y squared. And we're going to take that from y equals 0 to y equals 3. Right? You don't actually have to write the y equals, but at this point it might be helpful. All right, so that's 21 times 3 plus 6 times 3 squared. Take away 0 because the whole back half will be 0. And so that is 54 and 63, so that's 117. Now let's look at that in Maple for a second, because we want to learn how to find this in Maple, and we want to learn what we're looking at. Okay, so 2x plus 4y is actually a plane. Oops, I kind of have my x and y axes tilted. Sorry about that. Let me fix that. Oh, I see why I did it now. It's kind of hard to look at. Okay, so it's this kind of plane going like this, right? So tilting up as we move along. Okay, so we have this plane, and so what's happening is you have a piece underneath it that you are going to look at. And we actually have it here from 0 to 3 for the y and from 2 to 5 for the x. So we're kind of looking at that shape, that volume of that object right there between the plane down here with gray and that plane up here with the red. All right, so I've drawn that on the paper here. So we have a rectangle on the xy plane that's going from 2 to 5 for the x and 0 to 3 for the y. And then On the plane, the diagonal plane, that is z equals 2x plus 4y, we have some piece of that that casts its shadow down onto that rectangle. And what we're doing is we're finding the volume, if you will, of this whole piece from the xy plane all the way up to that diagonal plane. The volume of that piece is 117. Now, if this was in, let's say, centimeters, for example, it'd be centimeters cubed or inches cubed, right? So if this would be if x, y, z are in centimeters, right? Then the volume would be 117 centimeters cubed. All right, now the next question would be, we did x first when we did this, right? So the x was nested inside, so we did the x first. But what if we did the y first? Would that change the answer? So let's look at that method down here. So we want to take that same integral, but we want to do it with respect to y first. Okay, so let's see here. Integral from 2 to 5, and then I'm going to do the inner portion first. I'm just debating my color here. So I don't want to use the same color. Here we go. Let's do this one. All right, so we're going to do it with respect to y. So that'd be 2xy plus 2y squared from y equals 0 to y equals 3. And then dx, because dx is the part we haven't done yet. All right, well, 3 and 0 is easier because 0 is going to make nothing happen. So this is really the integral from 2 to 5 of 2 times x times 3 would be 6x plus 2 times 3 squared is 2 times 9, so 18. So you can see already how we start making our lives a little bit easier with these by doing some of the math in our head. And then, all right, now I'm going to integrate with respect to x. So that would be 3x squared plus 18x. I'm going to take that from x equals 2 to x equals 5, right? So that would be 3 times 5 squared plus 18 times 5 minus 3 times 2 squared plus 18 times 2. This is 75 plus 90, take away 12 plus 36. So getting all of that done, it's 117. Same as above. All right, so that leads us to a couple things. One, a very important theorem, which is that for a double integral over a rectangular region, the order of integration doesn't matter, right? Now, it's very important that you notice this is only for a rectangular region. It is not for other regions, so we'll have to be careful when it's not a rectangular region. But the integral over that region, R stands for the region, of f of xy, and the way we abbreviate it is dA, right? A being the area of the rectangle down here that's being formed, right? So the integral, sorry, my R looks like an A, and I want to make sure it's an R. The integral over the region of f of xy dA is either from C to D, from A to B, f of xy dx dy, or from A to B, C to D, f of xy dy dx. The order doesn't matter for a rectangular region. So I'm just going to make a note over on the side that this is only the case for rectangular regions. It is the case for something else as well, but they're related. But once we start having regions that are not rectangles, which will happen very quickly, then we'll have to be much more careful, right? Because then all bets are off. You can reverse the order, but you'll have to be careful when you do it. It's not that it will find different numbers for you. It's that you have to be very cautious when you do it, particularly in regards to your limits of integration. So if it doesn't matter, then you can just go with whatever, right? Well, true, but sometimes you want to choose the order of integration to take advantage of an easier integral, right? For example, let's look at this one right here. Yes, I could do dx first or I could do dy first, but if I looked at this, I'm thinking x is in both of these places. X is here and over here inside that secant squared. Ugh, that's a little nerve-wracking. That's a little dicey. So I think it would be better to do y first because y only appears in one area, right? Secant squared of x, y. So you pick ones that make your integration life easier. All right, so let's integrate this. So we're going to integrate this from, now the x goes from 0 to pi over 3. The y goes from 0 to 1. All right, so x secant squared of xy dy dx. Okay, so does the fact that I'm doing this with respect to y make things easier? Well, yes, because the integral of secant squared is a known integral. It's tangent, right? So the integral of secant squared, so let me do this, 0 pi over 3. This inner piece here, right? The integral of secant squared is tangent. So tangent of xy. And then I'm going to take this from 0 to 1. Now, what about this x here? Will this work? Well, remember that the derivative of tangent is secant squared of xy times the derivative of the interior. But the derivative of the interior is x. In other words, I'm doing sort of a little u substitution. If u is x times y, then the partial derivative of u with respect to y would be x dy. And I have an x and a dy right there. So if you will, what I'm really doing, if you want to think of it this way, is the integral of secant squared of u du. Oh, sorry. I kind of fudged two things together there. It's really the partial with respect to u is equal to x. I was doing the derivative and then you multiply by the differential. Sorry about that. All right, so integral of secant squared of u du is tangent of u, right? So that's what I'm doing, right? I'm kind of doing a u substitution on the side a little bit, right? So the integral of secant squared is tangent of xy, and the derivative of tangent of xy would be secant squared of xy times x, so we're good. And then I haven't done my derivative with respect to x yet, so I'm assuming my integral with respect to x, so I'm leaving it there. So this is 0 to pi over 3. The tangent of, remember these were y values. If it helps, you can put little y equals in there. This was tangent of y equals 1, so x minus the tangent of 0. But the tangent of 0, right, let's think about our unit circle. Tangent is sine over cosine, right? So if you have 0 as your angle, the sine value would be 0, the cosine value would be 1. So the tangent of 0 is 0. So this whole piece is gone. And then we're taking this with respect to x. All right, so then the integral of tangent with respect to x. So the integral of tangent is a known thing, but we don't actually need to know it. We can just use Maple to do it. I can write it down, but we're not going to actually bother. It's the natural log of the absolute value of the secant of x from 0 to pi over 3. It's one of the more obscure ones that you probably had in Calc 1, so it's not a big deal. And so you would just take the natural log of the secant of pi over 3 minus the natural log of the secant of 0. And of course, we're just going to make Maple do this. We're not going to find this by hand. Nope. Speaking of which, I should show how to do this in Maple. So when I want to find double integral, I tell it to do the integral command, int, and then I typed my function in, right? And then I said, I want to take it from x equals 0 to pi over 3 and y equals 0 to 1. And and it tells me that it's natural log of 2. If I want a numeric answer, a decimal answer, I just typed comma numeric afterwards and it came up with a numerical answer for me. Oh, and for the record, it doesn't matter what order you go in. This was the previous examples, but it doesn't matter if you go x equals 2 to 5 and then y equals 0 to 3 or vice versa. It's going to give you the correct answer no matter what. And if you're interested in a picture of what's going on, this is what's happening. So we have this three-dimensional surface. This rainbow surface is the x squared, or excuse me, the x times the secant of xy squared. And therefore, what we're finding is the volume between the xy plane, that section of the xy plane, and that surface. So that space in between the xy plane and that rainbow surface, that's what we just found the volume of. So this is the natural log, I should say it's equal to the natural log of 2, which is approximately 0.693. And of course, we would state that we found this with computer, right? Maple is how we found that. If x, y, z are in inches, for example, then what we actually found is inches cubed, right? But that's only if we were given that they were inches in the first place.